and I'm recording this for posterity. So we're going to talk about Project 2 today. Hello, I'm Arpaci-Dusseau. I feel like I should record something like that. Anyway, so we're going to start talking about P2. Everybody excited about Project 2? Oh, I like it. Some enthusiasm. Good. So welcome. I know it's just another day in class for you, but look at all these people that are here with you. How many of these people does each person know in here? Probably not that many. So look around. Once in a while, introduce yourself to someone new. You never know. There might be like a best friend sitting next to you that you just never spoke to. So introduce each other. Say hello once in a while. Okay, so that's my advice for the day. P2 has two components. Let's look at those really quickly, and then we'll just look at some code, and then we'll break, and you can begin your struggle. There are two parts to P2, a shell, which is where you implement a little Unix shell which has some various features. It is not as fully featured as the shells you use today, so that may be a confusion actually. You'll wonder if a particular shell feature needs to be implemented because your shell does it. Just read the details of our shell carefully and you'll see whether you have to do it or not. And then we'll go into the the XV6 kernel a little bit and look at a scheduler. We talked about scheduling policies in class a little while ago. Now you get to implement a very simple priority-based scheduler. So we'll look at some code in there too. And instead of going through the details and just reading text to you, I thought we'll just start by doing some code, if that's okay. How's the readability of that size right there? Okay? Okay, it's great even. I like that. Everyone's in a good mood. It's Friday, I guess, right? All right, Friday, yeah. I wake up on Friday and I'm like, this is a great day. It's Friday. Oh yeah, I have class. So Fridays don't feel the same to me. But no, actually I like class. Okay, so let's go ahead and start a little program here. And to build a shell, we're going to have to learn about the process creation API is really what we're going to be studying in a little bit of detail today. We talked about processes as running programs, and we talked about what that is. It's your program when it's in execution, so it has, at a given point in time, it has the program counters telling you where it is in the execution of the program, and it has memory state and all that sort of stuff. We have an abstraction of what a process is, but we haven't talked about the API. We leave that to this project specifically. And specifically, we need to be able to know how to do things like how to create a new process, how to get that process to be the exact running program that we want it to be. When you type something at a shell, for example, when you type the command, say ls to list the files in the directory, the shell has no idea what ls is. It's just trying to find a binary program called ls and then run it. And then it runs that program and does whatever that program is supposed to do. In this case, ls, as you know, lists the files. So if I type, this is a shell command, which, if I type which ls, it tells me, oh, that's not that useful. Let me unalias ls, and then let me type which ls. What it tells me is that when I type ls, what it's really running is this program in the root directory of this file system in a directory called bin. There's a program that the shell figured out is called ls in that /bin directory, and it's going to run that. And when you run ls, of course, with some arguments, it'll do things like run the program. The shell will run the program with those command line arguments. And then it runs it, of course, and then we're done. So in any case, back into the program we go. I don't know if I mentioned this before. Sometimes somebody asks me, how do I hop back and forth from my editor to the shell and back again? I'm in an Emacs session right here. For those of you who use Emacs, of course, you can use whatever editor you want. And when I want to get out of Emacs, I just hit Control-Z. Control-Z puts Emacs to sleep. And then when I want to start running it again, I basically just hit FG, which stands for foreground, make that some process run in the foreground again. And then it just pops right back up. So I can easily kind of hop back in and out. There are many different ways to do something like that, but you should generally have a good way to hop around from editor to terminal by hand, automatic, without having to reach for a mouse or do something very slow like that. You should be always thinking about little efficiencies that make you faster, and usually that means making it so that you only have to touch the keyboard and don't even have to touch the mouse to do things. Okay, So the first thing we're going to do is we're going to create a new process. Let's print out something first. Hello. That's pretty exciting. And then let's print goodbye. So this is not an exciting program, but we're going to do something first, which is we're going to create a new process from within this process. So we're going to compile main and make an executable, main.c. We're going to make an executable called main, and then we're going to run main. But main itself, when it runs, is going to create another process, and we're going to figure out how it does that. Does anybody know the Unix API for creating a new process? Who knows that? Fork? Yeah, fork. Yeah, fork. And that's a historical name. Somebody a long time ago, they called creating things to fork and then to kind of connect them back up. They called it a join. Why that is, again, it's lost on me. I'm sure there's a good reason for it, but there's probably some paper that was written a long time ago. So let's look a little bit at the fork man page. Fork is a system call. It's supported in xv6 as well as on every Unix system. And you see we're going to need a include file, and then what it tells you is fork creates a new process, and it does this very strange thing. It creates a duplicate of the calling process. So that's a little bit strange, and we're going to see how to use that in a second. But it's going to create, essentially, it's the only system call that's like this. When you're running along, you call fork, it looks like it's a procedure call. And usually when you make procedure calls, you expect the procedure call to go off and do something, and then for it to return. What fork does, with the help of the operating system, is you call into fork from, say, main, which is a process that's running at that point, and it actually creates a new process, and then both of them now exist. The parent, who is the creator of the process, and what we call the child, which has just been created. Now there's two processes that exist. They both look like they're running that main program, and they both return from that fork call. So it's very strange. You go, one process enters, two processes leave, right? So that two processes return from the fork if the fork is successful. So let's go ahead and look at that a little bit. Let's go ahead and do that. Let's just make it an integer. Okay, so we're going to start up. We're going to call fork. We're going to print goodbye. What is this program going to print when we run it? By what I said? Hello, goodbye, goodbye. That's right. It's going to say hello, goodbye, goodbye, because it's going to start up and then calls hello, and then when you call fork, now there's suddenly two processes. And notice that second newly created process, it doesn't start at main at the beginning. It starts as if it were just returning from fork as well. So they have two runnable processes now. The scheduler may run one first or the other. It may interleave them in whatever way the scheduler wants, as we learned about, and then it's going to return, and they're each independently going to print goodbye. Okay, and at that point, the important thing to realize, creates a new process is created, as well as, remember, there's a new entire virtual address space, right? When we create a new process, it means we have our own address space. It looks exactly like the parent's address space at that point, except for one little detail, which we'll get to in a minute, or a few details, but one important one. But it's in its entirely own address space, so if it starts manipulating variables or whatever in its own address space, it's not going to affect the parent, and if the parent starts changing its variables and so forth, it's not going to affect the child. Does it make sense? Okay, so let's go ahead and compile that. Okay, it tells me not to do that because I forgot to do that. And then I don't use RC, so I'll go ahead and just return it so it doesn't complain. Okay, let's see if what I said is true. It is. Okay, so that's fork, and already that's very strange, right? You just create a copy, and that's not generally useful. You don't want to create a copy of whatever you're running. For example, the shell, which is a process, when you type ls, you don't want it to just say, okay, I'm creating a new process. You want it to run ls. I'm just going to run the shell again. That's not what you would want. You want to be able to run ls or another program entirely. So we're going to build towards that, so don't worry about that. Okay, so one thing we're going to pay attention to, though, is when I said this process is a copy of the parent. One exception, one difference, and I'll just put it in the comments here, is the return code. So let's go ahead and print that out. Return code, let's just print an integer here, RC. And it turns out that return code is critical because the return code is going to allow the code itself that we're writing to differentiate between whether you were the parent who returned from fork or you were the child that returned from the fork. Does that make sense? So we can, in the codes, check the return code and say, by looking at the return code, we can see exactly what we expect. And what we can actually do is read this, rather detailed man page of fork. But you can see on success, the PID of the child processor is returned to the parent, and 0 is returned in the child. Okay? So in the parent, the return code is going to be some number, like 30,000 or something like that, whatever the PID of the newly created child is. And in the child, you're simply going to receive a 0. And then on a failure, you're going to see a -1. Okay, so we're going to use that in the code to differentiate what's going on. So let's, in fact, just go ahead and use that in the code. So if it equals 0, that's an interesting case. If RC is greater than 0, that's an interesting case. Again, this is the child. This is the parent. And then else, well, that means we have a failure. So we'll go ahead and print a failure message or something like that. Okay, and then maybe we'll exit. Just why not? Oh, no, I'll just print it. We'll exit anyway right down here. Okay, and then let's print something out in the child. So let's print child, something like that, and let's say %d. Let's print out, well, you know what we should print out? Let's print out the PID of the child. And if you know your simple system calls, we're going to print out get PID. And in the parent, let's print something else entirely. Let's print out the return code. Return code was, and then go ahead and do that. Okay, so does that code make sense? And I'm going to remove some of these comments as we go so you can just really see the code. And I'm going to make it compressed like this. I wouldn't necessarily do this, but it's nice in this classroom setting to be able to see everything in one page. Okay, any questions about this code? Make sense? You could write this code so far? Yeah? Okay, let's see if we did it right. Well, something looked okay. Okay, and we see here the parent ran here, the child ran here, they each print goodbye, and the parent, you can see the return code was 7167, and you can see the child printed its own PID, which thankfully matches. It says, yes, I am PID 7167, and we know, of course, the child's return code was 0 because that's what the code told it to do. Does that make sense? It's pretty weird. I mean, at least I remember finding it strange when I first looked at fork, and then another system call we're going to use in a second, exec, is also a little bit strange because they look just like typical, like a function you would call, but they do this very strange and huge thing, which is to create a whole new running program, and it exists just at the moment of returning from that fork call. Okay, questions? Yeah. Will the fork fail? There's limited resources in the system is a common case. So like in the XV6 kernel, it's pretty easy to get fork to fail. There's a very small process table, and that process table has actually a fixed number of entries. So if you run out of entries, you can't create a new process. That's the typical case. You can see that it doesn't have any arguments, so it doesn't say like a bad arguments is not how it's going to fail. And there's probably a few other cases where it could fail, but those are a little bit more detailed. So the question there, just if you couldn't hear it, was when does fork fail? Yeah.
Could you share variables like I'm going to open a file pointer and I'm just going to call fork?
Great, good question. So the question was about what is shared between the parent and the child, and they do share some things, and we'll talk about what they share in some detail. But the most important way to look at it, it is a separate address space. So the most important thing, if it's variables and everything like that, are completely independent. Once you have a separate address space, that means, and you can think about how this would be implemented, and we'll in fact look at how this is implemented in the next project, or actually the next project. we'll look at how fork is implemented because we're going to use fork to actually create threads, not processes. But long story short, how would you implement something like this? You're taking all the memory of the calling process and you're logically making an entire copy of it and making a brand new address space which has all the same stuff in it. So then when I modify, if I'm the child and I start modifying my address space, it's not going to affect the parent and vice versa. Now they do share some things, but let's maybe not get into the details of that because it'll probably be more confusing than anything else. So that's a question about sharing. Other question? And you could prove to yourself that they are independent by declaring a variable and just modifying in one and see if it affects in the other, and it won't. They'll just be independent variables, but I won't do that here. Okay, other questions? Okay, so now we want to do something else. We want to constrain a little bit the order of when these run. And in particular, what we want to do is we want the parent to be able to wait for the child to complete its execution. Okay, so to do that, we have to use a different system call. We're going to use, it's called wait. And we'll just go ahead and use this here. And I'll just show you how it's used instead of making you read the man page. But basically what it's going to do is we'll ignore everything. Well, let's read this one part so you can see what it returns. So on success, wait returns the process ID of the terminated child. That sounds kind of grim, doesn't it? Of the terminated child. So like I said, operating systems are grim. So let's, child PID here is, let's call wait. And then you can get more information about that terminated child if you want to, by passing in an argument, but we're just going to pass in null. And let me make sure the top has the right include files. So let's go ahead and do this. So what wait will do is when the parent calls wait, it goes into the operating system and it basically says do not return until some child process exits and is finished. So when I'm thinking about this program then, and I'm thinking about the output, what am I going to see on the screen? Yeah.
You're going to see child's contact printed out first and then
Yeah, so the answer was you're going to see, well, you'll see hello first, and then you'll see child printed out first. And in fact, then you'll see the child print goodbye. Then you'll see the parent return from wait, print out the parent print out here, and then print out its goodbye. If we don't put that wait in, what can we say about the output? It's not deterministic. That's right. We don't have a way of knowing anything about the order because to know the order, we would have to know exactly how the scheduler makes decisions at any given time, and that's very hard to know. We have two runnable processes here, parent and child. You don't know which is going to run first. One might run first, the other might run first. In fact, if we ran this as an experiment multiple times, you would probably see both orders. So let's see if that's true. And let's go ahead and quickly just make, you have to make a make file for this project. Who's made a make file before? Most of you. Okay, let's make a really bad one that doesn't do anything for us. But at least it makes this so we can type make. The only important thing about make files is you have to remember to add a tab when you're doing one of these execution steps. Otherwise, it gets very confused and tells you life is terrible. So let's see if that worked. It didn't because I didn't use CPID. So let's go ahead and use CPID. In fact, let's go ahead and print it out here. This telling us which child is going to do whatever. And let's see if in fact it did work. Well, this says hello and then child. And then the parent now says, yeah, the CPID, the child that exited was 7228. And we can see then the second goodbye is printed out. Okay, so now we have an interesting piece. A parent can, and what you can, I don't know if you're paying attention, but I assume you are. If you're paying attention, if you're paying close attention, you're getting a sense that we're kind of organically building towards what a shell does. When you type a command, there's some parsing of the command. We haven't done that yet. Then the shell is going to call fork, to create a new process. Then we're going to figure out how to run in that process in a second. We're going to figure out how exactly to run the command that you want, not just a copy of the shell, which isn't that useful. Then what we're going to do is the parent, in the typical case, waits for that command to complete before returning control to you to let you type your next command. So the parent, you can think of when it's a shell, is printing out, well, tell me what your input is. And then you type the command. Then it goes off and does that command in a new process. And then when that command is done, it returns control to you to run again. And therefore, that's a little part of a shell, is doing a fork and then waiting. Question? Question?
Can you call wait without calling fork?
Well, you can call any system call. What will it do? Yeah, it won't do anything useful. Yeah, and there's if you want to look at wait, and actually it's slightly more flexible cousin wait PID. You can look at all the different error cases. What happens when you call this and this doesn't happen, and can you get it to return? What will it return, and so forth and so on. So I would just read the man page for details on things like that. But in this case, you'll just be using it in a very typical way, which is you'll be calling fork in your shell in order to create a new thing, a new process, and then the parent will be waiting for that. There's one case in a shell where you don't wait. How many people have used the shell in that way before? Where the shell does not wait for the child. What's that case? Yeah, when you put an ampersand at the end, most shells will background, they call it, the process. What that means is it's going to start running the process, but the shell isn't explicitly going to wait for it. Rather, it's going to return control to you right away so you can keep typing and run something else. We're not going to implement that. It's actually fairly easy to implement if you wanted to. Other questions? Yeah?
Why do we return RC?
Why do we return RC here? Oh, I don't know. Return 0. Because before it was complaining, before it was complaining about that I wasn't using RC, and I just said, okay, return RC, because I'm lazy. Yeah?
What happens if you call fork twice and then call wait?
Yeah, so if you call fork twice, living very dangerously, I like it. You're a bold programmer. That's okay. You can call fork twice. Now you have to think about how you call it twice. Are you calling it in the parent? Because if you call it twice, maybe you'll call it one extra time, because then if each of you call it again. So you can create as many processes as you want. Wait will return when a process exits. So
How does it know?
it knows which one exited, and then it'll return. It doesn't know. You're not waiting for a specific one. You can use wait PID to do something more specific than that, but wait will return when a child of the current running process returns or exits. Yeah.
If I add another fork right after that,
Yeah.
then just keep on creating.
If you add another fork here, like this, well, that would mean, so the parent calls fork, and then now we have a parent and child. They each return from fork. Then they each call fork. But then we're done with all this forking, as they say. That's as close as I get to vulgarity in this class. Many years ago, it's a funny discussion, right? You're talking about parents, children, and forking. So I realize I very generally don't use that phrase. I just try to say, we call fork. So, and now you'll never look at that quite the same way. Okay, my apologies. That was more vulgar than I wanted it to be. Okay, so no, I don't think it'll call it infinitely. You can get into a case where one second on the question, you can get into a case where you get in a loop and start calling fork repeatedly, and then suddenly it's actually kind of an attack on a system. It's called a fork bomb, and you can use up a bunch of the resources, make it so it's very hard to create new processes. So be a little careful with it. It's not a huge problem, but you can imagine that is an issue, actually. Question?
That was actually my question. But also, what is the argument to wait?
Yeah, so I'm going to kind of defer these things to reading the man page. But here you can find out a little bit more about the status of the exited process child that just exited. And the way you do that is by passing in a pointer to an integer, and that'll get filled in, and it'll tell you like the return code of the child. And then you can find out more stuff. There's more control available, as I said, via wait PID. But we don't really need that here. Okay, good questions. Okay, now we're going to do something a little bit more interesting, a little bit more complicated, which is in the child, instead of running just the shell, we're going to do something else. We're going to run a different program entirely. We're going to start a brand new program. And this is, in fact, how a Unix shell, when you type ls or main, as I've been typing, or any of the things that you can think of typing at a Unix shell when you're creating a new process, this is how it does it. It creates a new child by calling fork, but then it calls this other system call exec to do something new. So let's look at, and we're going to use a particular variant of exec. There's a few different ones called exec v, and that's what you'll be using in this project. So let's go ahead and look at that. You can see we need to go ahead and copy that. And then we have exec v down here, which says it takes two arguments. The path, so the path is the fully qualified, hey, what program are you running? So that should be something that looks like /bin/ls. And then it takes argv, basically, which is going to be passed directly to that child. So argv 0, 1, 2, 3 includes the name of the program you're running and all of its arguments in separate, argv is just an array of strings, or an array of, you can think of it as an array of pointers, but they're just strings, an array of strings, and each string is an argument to your about to be run program. Does that make sense? So let me go ahead and make sure I have this going. Sorry. Yeah, I already have that. And we want to pass a path. And we're going to create that by making our own my argv, we'll call it, and then we'll go ahead and call it. Now, just like fork was strange, when we called fork, remember, one process entered, two processes left, right? In exec, we have the opposite, which is when you call exec, well, it's not the opposite, but when you call exec, if it's successful, it never returns. In fact, what exec does is it says, I want to run this, I'm a process, and I want to run, as described by this argv that I'm passing to you, I want to run this brand new program. And what you should do is basically get rid of my entire address space, make a brand new address space in there, initialize the stack and the heap, and the code should be brand new code, not this thing that I'm running right now, and then start at the main of that about to be exec program. So that's a little bit weird. Let's go ahead and do something like that. So we'll do my argv here. Let's say we're going to fill in a few different values here. And then let's go ahead and fill in the entries. Let's say we want to run, we're going to use string dupe because we need to allocate some memory. String dupe does that for us. And when you pass a string, you could also call malloc and then do a string copy into that, but string dupe does that for you. And let's say we're going to run bin ls. That seems to be my favorite program in the world to run, is to just list files. So I'll just keep doing that. And let's pass it a few arguments, -l, -a. And then the important thing about this argv array is it's expected, we don't pass in a size for it, so the system has to know where does it end. And the way we let it know that how it ends is we make one value past the useful parameters a null valued parameter. Does that make sense? So I've declared here on the stack this myargv array. Each entry of the array I've now filled in with bin ls, -l, -a, and then in this case null terminated. And this is important. Now exec can fail, so you have to think about what to do when it fails. Failed. But in this case, we're not going to do anything too much. In fact, I should probably just do this because people will otherwise, in the shell, if exec, you will use exec incorrectly. If you pass like the arguments incorrectly, like let's say you forget the null termination here, or somehow you don't pass in a legal program to run, that's all fine. But it means exec fails, which means it's going to return. And you should just remember to go ahead and exit, and maybe with an error code. Just go ahead and do that. Make sure to exit after exec fails. If you don't do that and you're in your shell, you'll actually end up creating a bunch of shell processes every time you call fork and then you exec fails, you forget that it's not going to ever properly exit. So that's just something to be wary of. Okay, and then we'll have to add a little bit more to that to get this to compile and not complain. I bet this. Okay, so any questions about this program right here? What the child is going to do? Yeah?
Next question. So, exec doesn't impact.
That's
So
correct.
Never printf.
Great. So this printf will not be called unless I did it incorrectly here. That's correct.
So where exactly does it go?
Well, exec goes into the operating system. The operating system says, okay, this process, which is the child process, it doesn't seem to want to be itself anymore. It wants to start all over. It's kind of a rebirth. And this should be an exciting time in the life of a process, right? It's throwing off its old clothes as main.c, and it's becoming ls.c or whatever, compiled into ls. And so it's just going to say, okay, how do I become this brand new process? And the way it does that is it finds the code part of the binary called bin.ls and it loads it into memory. And it finds some, initializes a stack, says get rid of all your old stack. Here's a brand new stack. Aren't you excited? And the process says, yeah. Well, that's internal to the OS. You don't see that. And then what happens is what's on that stack? Well, it's like about to call main. So it puts these arguments in argv and all that and puts that on the stack. And it sets up a little bit of an initial heap. And a bunch of other stuff happens. And then it returns from a trap into this brand new process. And all remnants of the fact, almost all remnants, not all, of the fact that it used to be this other main.c are gone at that point. Now, not all remnants, and we'll see how that's useful in a second too, but basically all. Other questions? Yeah?
So if you want to do something in the child after the completion of execute, how does the control actually return back?
Yeah, it doesn't.
We can't do anything.
Yeah, once you exec that's the program, and that's going to run to completion, and that's done. The only thing you can do is the parent can wait for it. But you don't get to run again inside of here, below here. This only runs if exec v failed. So that is the end of our control, our life. We have a new life upon us. Like I said, it's a good time. Okay, so shall we see if this works? So if we should print out hello once, that's the parent. The child then should run and print out whatever ls would print out with -l and -a as its flags. This will not happen here. And then the parent will say something afterwards, like, oh, my child PID was whatever. And I forgot to do something. Okay, good. String dupe requires us to include string.h. And then let's go ahead and run it and see if it works. And you can see it did. Here's hello. Here's the output of that program. Here's the parent once that program's finished saying, yes, that program is done. And then the single goodbye now, right? We're down to a single goodbye because that child never goes down that other path and prints out goodbye now. It's gone. Exec got rid of all that. It's just done. Very weird, right? These are two weirdest system calls are fork and exec. And there's a really important reason that fork and exec are separate like this, and we're about to learn what that is. But it's weird because if somebody said for you, like if you said, hey, I'm writing an operating system, and I want to create a new process that's running ls, you'd say, okay, what should that API look like? You'd probably say, well, it should look like this, create process or something like that. And you say, I'm going to run ls, and maybe there's some arguments and so forth and so on. And that's true on some systems. They have a create process, and it actually tends to be very complicated. Fork and exec work together to do that, but the separation is very powerful because between the fork and the time we call fork and the time we call exec, we can do a few other things to set up some stuff for the about to be exec process. And we'll see what types of things we can set up to change its environment a little bit that makes it run a little bit differently. So for example, when I type ls myself and then I do this, like a redirection into temp file, what happens? What does this redirection do? Who knows? Okay, tell me. What's it going to do? Okay. Great, it puts the output in the file. And let's see if that's true. Looks like it. Bunch of files. Okay, and then let's remove that because why not? Okay, now the question is, of course, well, when we type that, how does the shell do that? And does ls know about that? Does the file, who knows that that's happening? And the cool thing about the Unix approach, which is actually inherited from some early operating systems, but the very cool thing is ls is not changed here. ls doesn't know that it's what it's usually prints to the screen, right? Whatever you're seeing, it prints to the screen. And that's what it's doing. That's what it thinks it's doing here. But what the shell is doing is it's setting up what normally prints to the screen to actually be written to a file. So the shell sets that up and then runs ls, and then ls just runs, and printing is just writing to a file descriptor. Unix uses file descriptors for almost everything. You use them to write to files, which makes sense. They're called file descriptors. You use them to do network communication. Then we tend to call them socket descriptors. You also use them to print to the screen, to write to a special file descriptor called standard out. That's file descriptor 1. And so what printf is really doing internally is writing to file descriptor 1. So if we just change what file descriptor 1 is, we can make it so the program that's about to be run, instead of printing to the screen, writes to a file. That's very weird, but very powerful and very cool, and what makes the whole separation of fork and exec so interesting. So let's do a little version of that. So in the child, what we want to do is, let's go ahead and say before exec, we want to change something about standard out. Okay, so we could, of course, just close standard out. And let's go ahead and I guess you could probably do a man on standard out. I wonder if there is a man page, yeah. Okay, so you could read more about it if you want to. But this is the one I want, which is not that convenient. Standard out file number. So every Unix process that's running has before you even do anything, has 3 file descriptors that are open and used. 0 is standard input. When you read from standard input, it means you're reading from what maybe the user is typing in. That's file descriptor 0. Standard output is when you want to see something on the screen. It's normal output. That's written to file descriptor 1. And standard error, which you usually think about just writing to, but I bet you can read from it too. A standard error is used for error output, and you've already seen that. You can do fprintf standard error instead of standard output, and the reason it looks like the same to you on the screen, but you can use some shell fanciness to redirect like standard error to one thing, standard output to another, and see if the program's printing error output versus kind of normal typical output. So if we close this, what's going to happen when we then exec ls? Well, the important thing is when we do this exec, that doesn't change anything that doesn't restart our standard input, output, and error. It actually just inherits them from the child that's calling exec. So this kind of gets to your question that you asked earlier about, what do we kind of keep along? Well, when we call exec, we keep exactly the file descriptors that are in place already. So if we've closed standard output, what's going to happen when ls tries to print? Yeah, it might throw an error. If ls is paying attention, it'll throw an error. So let's see what happens. And you can see, in fact, that's true. Bin ls says write error, bad file descriptor. So that's no good. Poor ls, trying to write some nice ls output for us, not able to. But here's a weird thing that we can do. And this is the weird thing that you'll be doing. And there's different ways to do this, but I kind of like this way, it's the simplest way. When you call open to open a new file, and not fopen, by the way, you have to call open in this case. We want to open, well, maybe you could use fopen, but let's just use open, the direct system call. Open is a system call. It takes a file, let's call it file.standardout or something like that. It takes some flags. Well, I know what they are, but you can read them up on them yourself. create means please create this file. Truncate means if it exists already, truncate it. And let's go ahead and say we can only write to it. And then the third argument is optional, but it'll make for its permission. So let's go ahead and look at what we want for that. Probably the easiest thing for the man page there is make it readable and writable. So let's copy one of these. And I never remember these because they're confusingly named. So this looks confusing, but if you read the man page for open, it's not that big of a deal. But what we're doing now is we're opening a file and we're calling it temp_file.standardout. Now what the guarantee given to us by the operating system is when I'm opening a file, the operating system is going to try to open, it has to find a free file descriptor. A file descriptor is just an integer, 0 through some large number that you could have, and you can read and write to different file descriptors to read and write to different files. Now remember that standard input, output, and error are already file descriptors 0, 1, and 2, but we closed standard out, right? We closed file descriptor 1. When the operating system, when you then go to open a new file, what it does is it looks, starting at 0, is 0 available for me to use as a file descriptor? Well, it's not going to be because standard input is already in use and open. Then it's going to go to 1. And at 1, it's going to say, oh, 1 is available. So I'm going to use file descriptor 1. So when we open this file, temp file standard out, then what I'm going to do is it's going to create this file. It's going to be associated with file descriptor 1. Then I call exec. Exec starts this new process. The new process starts printing. Printing internally calls write to file descriptor 1. So where is our output going to magically go? It's going to go to this file. Now how weird is that? But that's how some magic is done. But I forgot something because I forgot to include all these things. Don't remember which ones, maybe all of them. So let me go ahead and do that. Systype, syswait, okay. Okay, let's see if it does something. So let me make sure that nothing is there called file.standardout. No such file or directory. Let's run main. Did something. Let's cat the output of this file. And magically it appears. So that, without the parsing, is how redirection is built by a shell. A shell notices you type something like this, and it says, okay, I'm going to fork to create the process that's going to be the program ls. Then I see that there's this redirection going on, so I need to, in that child, close its standard out, open up file, and that's all I need to do for ls to run. And notice the beauty of that. ls is not changed in one simple way. You don't have to pass a new flag to ls to say put its output in file. You don't have to tell it anything special at all. It just works. ls just calls printf and it's magically redirected. Questions about that? Amazed? Who's amazed? I'm amazed by that. Okay.
Does fork also not change file descriptors? Like you close it and then you call the child as child's file descriptors?
Yeah, so the question is about what changes on fork with respect to file descriptors. There's a lot of detail in that I could give in that answer, so I'm going to not give a good answer right now. But the best place to read about that sort of thing is here, and unfortunately, you can see actually there's a long list of stuff you have to read about exactly what's inherited and what isn't. And so, in fact, even me giving an accurate answer would be challenging because it changes. But there's a lot of detail to that question so I'm not going to give a good answer right now. But it's something you can certainly read about. There's another question? No, just saying you're amazed. All right. Yeah, good. Other questions? Yeah.
So with file descriptors, like an index and just some array or something, because the context.
Yeah, so kind of asking the questions about, well, why do we have a file descriptor? It's just a way for us to efficiently say, when we call open on a file, instead of having to do it every time we read that file, and I guess maybe the generic way to think of it is you call open, you say, here's a file, I want to read or write this file. Then the system's going to go through a lot of work to figure out like what is this file? Where is it? Is it something with is it a network thing? Is it a file in the file system? What is it? Are you allowed to access it? It does a bunch of work like checking like that. And then once it figures out all that stuff, it's going to want to have an efficient way of tracking that. So when you do reads and writes, I don't have to go through all that process again. So there's basically just an open file table that you have. There's one that, you can think of, there's a per process, what descriptors are available to you at any given point. And then there's a lower level of sharing when like two people are sharing files. They don't share file descriptors, but you can be accessing the same file. So we'll talk about that more when we get into file systems. But yeah, long story short is it's just an index into some table that the OS is tracking for you. Yeah.
Sorry, I missed it, but why is it that when after I close center out and I open a new file,
Yeah.
the file descriptor is going to be the same as?
Yeah, it's just the guarantee here that this doesn't necessarily happen, but if you know that 0, 1, and 2 are in use, then we've closed 1. And the only guarantee you have from the system that it's going to start when you do an open, it's going to start at 0 and start going up until it finds a free slot. So when we've closed 1 and then we do an open, we're either going to get 1 or you could get 0 if 0 was also available. In fact, you would get 0 if 0 was available. And in fact, if you ever do an open in a program, I don't know how many people have called open directly and then looked at the integer value, you might always have wondered, why is it always 3 to begin with? Well, it's always 3 to begin with when I open a file because 0, 1, and 2 are already opened as standard input, output, and error. So that's something you'll see as well. Yeah?
Wait, for example, for the closing that's file descriptor.
Yeah, so all of that's a good question. All of this, when the process is done running, the operating system has to do a lot of cleanup. One of the things it's going to clean up is what open files you have and close all of them. Another thing it's going to do is it's going to remove all your memory from physical memory or reclaim everything from your address space. Anything you've created as a resource that isn't a long-lived resource, it's going to clean up. So it's the OS's responsibility to clean up. In fact, that's why you can write a perfectly working program that just opens a file and writes a bunch of stuff to it, and or maybe it just reads a bunch of stuff from it. Let's say, simpler example, and then it doesn't call close. It's not like the system dies because you forget to call close in your slightly buggy program. It's the OS will clean up after you. Now you should call close because it's just if you mean to close it, you should close it. But in this case, there's no way to close it, so we just rely on the system closing. It looks like it knows 0, 1, and 2 are open. It's going to close them. Yeah, one more.
If 0 is available and open returns file descriptor 0, isn't it weird that we're writing standard input?
Yeah, that wouldn't work very well. You wouldn't. Then the only thing that would ever show up in that file is if somebody was trying to write to standard input, which they generally wouldn't. So nothing would show up there. You can do it for input redirection. You can read from a file, and that's a kind of a different case. So for example, let's say I'm doing a word count, and I do something like this. You can see that's the opposite, right? If I do this, I'm putting the output of something into the file. If I do this, I'm taking the file and making it standard input for, in this case, the word count program. And you can see it prints the output of, it's, whatever the output of word count is, lines, bytes, etc. So you can do the opposite. We're just not doing that standard input redirection, if that makes sense. Okay. Weird stuff. So that's the shell part. And then, of course, how are you going to build a shell around this fork and exec and wait functionality is you're simply going to have a loop that prints out, a little shell prompt. Then you do a little bit of parsing. Then you figure out, okay, I'm going to do this in the child, so I call fork and do some stuff in the child. The parent waits, and then I continue. And that's pretty organic, that's how you build up a shell. And of course the difference is you have to take what the user typed and turn it into one of these argvs instead of just doing it by the hand like I did here, but that's not too hard. I assume that you'll be able to do that. Okay, any last questions on the shell? We have a little time left for the other part of the project, so I'd like to do that. Yeah?
If you fork a process and then you use exec to change the process, and you run a program like top of PS, how
How does it know that?
The process's name has changed, or does it not know that?
Well, the system, of course, knows because you're calling exec, and you're telling it exactly what program you're running.
I guess that's all set up by exec.
Yeah, it has to be, right? So exec sets up everything that needs to be set up so that this looks like this is this program that's running, not whatever launched it, which in most cases would be the shell. So that's how the OS knows stuff. Okay, so let's quit out of that. Let's go up into XV6 world. XV6 world, we're going to have to learn a little bit about the scheduler. The scheduler decides what process runs next. If we look a little bit at this assignment, which I'll show you here, we're just building a basic priority-based scheduler. It's really simple. It's simpler than like the multi-level feedback queue. Basically, each process has a priority. It's either 1, which is low, or 2, which is high. And the way you gain a higher priority is you just set the priority to a higher value, like 2, which is you should only accept 1 or 2. So this is not particularly a realistic scheduler that you would have, but maybe if you wanted somebody to have some control over, hey, what runs of my processes and which ones, if I have a high priority process, it should run. If there's more than one high priority process, they should round robin. And if otherwise, the low priority processes should run. So that's what the scheduler is. It's simple as that. There's 2 priorities. If anything's runnable at the high priority, it should run. Otherwise, you should run round robin between the low priority processes. That's really it. You have to implement 2 system calls as part of that. One is to set the priority of the running process, and one is to get info about all the processes. You can look at the structure here that you're going to have to fill in to see what's what with that. Here's the structure. And then we're going to go ahead and do some stuff over here. Okay, and we're going to run, of course, in our little environment. I always run it with -no-x. And one of the TAs pointed out to me a very nice little thing you can do. No-x means it doesn't pop up any windows. It just runs it right in the terminal. It's a little bit hard to exit if you don't know that in QEMU you can just press Control-A and then X, and that gets us out of there. So that's a very nice little thing. If you didn't follow that, I hit Control-A and then H for help, and you can see it says print this help. And then if you type Control-A, so hold Control down, hit A, let go of both, and then hit X, it just exits right out of there. Did everybody know that already? It's very useful. That way you don't have to have another shell open, and you don't have to use the X version so you can kill it by hand. You can just pop in and out of it. So, and that's also written on this page here of the project 2 scheduler. This, again, like some of the first XV6 projects, is not a lot of coding, but a lot of just being a little bit careful and understanding a few structures inside of XV6. So let's go ahead and look at some of those things that we need to understand. A lot of our work is going to be in proc.c. So let's look at proc. And in fact, actually, maybe a way to think of this is let's look at main.c. So at the end, remember we talked about when we boot a kernel, a lot of initialization happens. A lot of initialization. We initialize interrupts and trap vectors, blah, 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 all this stuff, disks. This actually is a multiprocessor OS, so it boots other CPUs, does some stuff with interrupts. And then it does 2 things right at the end. We talked about how we create a process in a Unix system. It's by calling fork, which is making a copy of itself. It's a cloning of sorts. Cloning is great unless you don't have anything to clone. So the first process needs to be created in a different way. And that's often, in the Unix world, that's called the init process. And so the kernel does some special work here in user init in XV6 to create that first process. And then init, once it starts running, it calls fork to create a shell, and then that shell is what immediately is running when you log into XV6. So at that point, 2 things are running. Init, which isn't doing anything, but it created the shell, and well, it's doing a little bit actually, but init creates a shell, and then the shell is what you start typing at. So right as we're booting and we're ending the boot sequence, we create this first user process, and then what we do is we call into the scheduler. And that's the part of the code that we're going to need to understand today. So let's just take a peek at that. Sorry, scheduler, yes. So in proc.c is where the scheduler is, and it's, I'll kind of make it a little bit smaller here. I'm going to just, for the sake of, oh, that's probably most of the shell thing right there. Okay, let me just, I'm just seeing if I can get rid of some of these comments so we can just look at all the code. Don't generally delete comments. That's not a good general thing to do. But anyway, let's take a peek at this code right now. So, and how much time do we have? We have a little bit of, we have plenty of time. Okay, so the scheduler is actually structured as 2 loops. And just for simplicity, you should keep it this way. Okay, so don't change the basic structure. You can add some more stuff, which you'll need to, but make sure to keep this outer loop is what I'm saying. So this is a forever loop. You can see what the kernel does is it basically says forever, now I'm going to be in the process of figuring out what to run and running it. Otherwise, I'm just going to be basically waiting around and waiting for something to become runnable, and then I'll eventually run it. So that's sometimes people essentially call that the idle loop. Sometimes the OS, early operating systems would just sit here and spin like that. They'd use the whole CPU just waiting, is something available to run? More modern CPUs will notice that nothing is runnable and move to like a low power state or eventually sleep altogether. But here we're just doing something very simple. We're just spinning until there's something runnable. We're not going to talk about why we're dealing with interrupts like this, but don't change that. We'll talk about that later. But then what you can see what the code is doing looks a little bit deceptively simple. It says, and you've already looked at this code a little bit, which is why it's nice to have a little warm-up project. It says, let's go through this process table, and then if the state is not runnable, well, continue, which means keep looking through this list. But if it is runnable, then I'm going to change this global variable proc to point to P. I'm going to call this routine called switch UVM, it's user virtual memory, which is basically going to say, hey, we're about to jump into this process, and it has its own user address space and all that stuff. When we learn about the VM system in XV6, we'll look at that code in more detail. But it says, hey, I'm about to run in this user address space, so get all that stuff set up, my page tables and things like that. I'm going to change the state of this process from runnable to running, right? Or from what we might call ready to running. And then to run that program, I'm going to call switch. And switch basically takes 2 arguments. We don't have to understand switch inside of here. But what it does is it says, it asks for where to save the register state of what's happening right now, and then basically what new register state should I restore and start running from. Now what's very strange about this piece of code, which all kernels have something like this, is when we're running to begin with, like the first time we're running, the scheduler is running on its own kernel stack. Each process that's running, when it runs in the kernel, it runs on its own kernel stack. There's a bunch of kernel stacks. There's one for the scheduler here, and then there's one for every process in the system. Each process has a kernel stack. And when you trap into the kernel and start running in the kernel from like when you do a system call in XV6, you start running on your kernel stack. That kernel stack gets created when your process gets created, and it gets reclaimed when your process exits. So that, what switch does is it enters on, running on one kernel stack, in this case the schedulers, and when it returns, what it's done is it's switched stacks. It returns on a different stack. So essentially, we jump into some code. It looks like a function called switch. But in the middle of running that, instead of returning right back to where we came from, we start going to wherever the registers are in this case, proc context. So wherever the state was saved of that process, whenever it last ran, that's what we're going to start doing. That's very weird. It means that the next thing that happens is not this piece of code. It means whatever is saved in these registers here, which probably tells us somewhere else in the kernel we were running when we stopped running that initial process. So it's very strange. So if you're trying to follow the control flow through this part of the code, it looks like it's just a loop and hey, just run this thing, run that thing, run this other thing. But it behaves a little bit differently. You have to study that in some detail. So you can look at switch if you want. It's in switch.s. And you can see what it does is it saves a bunch of registers, but then it does this stack switch here, moving ESP to a place where it's saved, and then moving where it had put its old one into ESP, and then it starts kind of popping stuff off that stack and returning to wherever that is. Now we don't know where that is, but commonly where you'll resume running, you can learn about that by looking at trap.c. And if you remember, like syscall, for example, whenever a trap happens, all traps and interrupts are vectored are jump to this code eventually in xv6. They run to this trap code. So remember when we do a system call, we jump to this code and it says, oh, it's a system call, and then I'll do this syscall code. But very common case in our scheduler when we're running two different processes are we may be doing something like a timer interrupt, right? A timer interrupt might happen that stops one process from running and starts another process running. So what does that mean? It means that a timer interrupt goes off, some stuff gets saved actually onto the kernel stack of the running process which got interrupted. Then we jump to this code eventually. Now it's not a system call because it's a timer interrupt, but you can go down here and see, what's going on with, we have a timer interrupt. And the most important thing that happens is when you do a timer interrupt, when a timer interrupt occurs rather, the calling process's state is saved, it's on its kernel stack, then you start running in the kernel in trap, then the code will call yield. And what yield will do, well, we can look at yield. In proc.c, what yield does is, well, it acquires this lock, and then it changes the state of the process that had been running from running to runnable, and then it calls sked, and sked, very weirdly, well, you can see they've had a lot of problems with building sked correctly, because what this code means is let's just, hey, if all these things aren't true, we're doing something wrong, and let's panic. That's what kernels do when they think something's wrong. They panic, which means they're going to basically crash. So a lot of times you'll see code like this in the kernel that says, hey, if this isn't true, something is horribly wrong. My assumptions about how this all works are wrong, and therefore I should stop operating. And there are milder forms of this where you can just report a bug and try to continue, but usually it means something bad is going on, and that's what panic does. There's a little bit of code here about whether interrupts are enabled. We're going to ignore that. But what yield does is it calls switch, and this time it calls switch. Remember we looked at switch. Remember switch is a very weird piece of code. You jump into it. It looks like it's a normal function call, but it says save my state into the first argument, the current running process's context structure, and then basically jump to a different kernel stack, which in this case is the scheduler stack. So that's pretty weird. What we're doing then when we're calling yield, we're going into the kernel, it looks like everything's going fine for us, but then suddenly we switch to a different kernel stack and when we return from switch, it's going to start running wherever the scheduler left off. So the way the control flow is going to work, if you think about the scheduler, the first time you come into the scheduler, it's going to go look through this process list. It's going to find a runnable process. It's going to set up its virtual memory stuff. It's going to switch to running, and then its state to running, and then it's going to essentially jump onto the kernel stack of that process that's about to be run, which is going to do a return from trap and start running that process. That process is then going to run for a while. When that process is interrupted by the timer interrupt, what's going to happen is it's going to come back in the kernel, eventually call yield. Yield's eventually going to call sked, which is eventually going to call switch, which is going to switch back to the CPU scheduler's kernel stack, which is going to return where? Where is that going to return? Let's do that one more time. You didn't know I was going to ask a question. So let's do that one more time. You're like, he's just talking. I'll listen to it later. Lots of details. Let's do it from the beginning. The scheduler starts up. The scheduler comes in here. It's looking for a runnable process. It finds one. It sets up some stuff, and by calling switch, it switches to the kernel stack of that about to be run process. And what that about to be run process is set up such that it's just going to return from the trap and unwind all that stuff and start running in user mode. Return from trap, user mode. That process is now running for a while. That process gets interrupted. A hardware interrupt happens. We save some state to the kernel stack of that process. We run into some code in trap. Trap eventually calls yield. Yield eventually calls sched. Sched eventually calls switch, which says, hey, stop running on that processes kernel stack and switch to the CPU scheduler's kernel stack and return from switch on the CPU wherever the scheduler had last kind of been running and entered switch. Where is that going to return? Right here. That's right. Wow, the answer is right in front of you. It's going to return from here. So it's very weird, right? The scheduler comes in here the first time, and then it kind of disappears for a while. Something runs for a while, eventually yields, eventually comes back to this and returns into here, which then can maybe come through this loop and run something else again. That's very strange. You'll have to play around with it a little bit. What you're going to be doing is basically staring at this code, trying to understand it a bit. You're not going to be switching things like the low-level switching code or how sched works or anything like that. You're just trying to change what gets chosen at a given point, and you just have a slightly different logic. You have two priorities you're going to be looking at, and you want to make sure if there's a high priority process that's runnable that you choose it. Otherwise, you should choose one of the low priority ones. And otherwise, it should be almost identical. Just keeping the same structure where you kind of look for stuff to run for a while, and then when you're done, make sure you kind of come back up here through the main outer loop. So that's all that project 2B is. Let me see if there's anything else that you need to know about that. As always, you can read the XV6 book. That's a lot of detail. You might not want to. That's up to you. And then other than that, the shell, of course, has a lot of details about exact error handling. The shell, we called it whoosh. All shells end in sh, so you just have to add something in front of it. And there's a bunch of details here, but really the basic shell of just in a loop, getting some commands, dealing with it. The path is probably the most interesting part you'll have to figure out. You can read about that. There's a redirection like we talked about. It's a little different than what we said, but you get the basic idea. That's most of the details of Project 2. So that is Project 2. Are you excited? Yes, still excited? Sounds a little less excited now. My woo counter says that's less excited. So sorry about that. Have fun.